Okay, good morning to everybody. I'm Daniele Strigaro, and this is a project coordinated by SUPSI and with other two partners, University of Moratuwa in Colombo, Sri Lanka, and IST in Pakistan. The project would like to help in finding a solution a solution to a lack of monitoring system in developing and low-income countries due to high cost of software, hardware, due to inaccessibility to local support, replacement parts, and also due to the missing of interoperability between data caused by protocols and so on. And in this field, we have some open stuff that we can use. We have open technology, open protocols, open standards, and here comes out the research. We are developing and integrating open monitoring system based on open hardware like Arduino. We are using the sensor observation service as standard to retrieve and share data, thanks to the IST, to the source software, which is open source. And then we also use open data portal like CCAN to share reports and data and so on. With this integrating monitoring system, we would like to know if it could be a solution to this problem. So we are evaluating the prototypes that we have developed. We are deploying the network to see if in a real case study these things works. And this is the system. We have mainly 3 layers. We have the hardware layer, which is basically the weather station. Then we have the communication layer, which is about this transmission of the data between the hardware and the service layer. And this last layer is the one who manages the data, who collects data, who stores data, and who shares the information. Starting from the hardware layer, we have developed 2 prototypes, the 4-ohm mode and the 4-ohm PCB. The first one is a modular solution based on common materials, and so it's easy to replace parts and things. But the negative aspect of this solution is that it needs quite time to be built, and also the connection are mere by wires, and also it needs more space. The other solution is the 4-ohm PCB, which is based on a PCB. The schema is open and can be downloaded, and it is easy to install, but also in this case we have some negative aspects because the components are soldered, so it's hard to change them, and also the PCB is not widely available in the market, and this is also a problem. And also it's a little bit more expensive. These 2 solutions share the same internal components. So in the main box, we have the Arduino as main controller. We have the RTC to get the date time, the OpenLog to store the data, to have a backup of the data that we are sending. And we are using the CM800 to transmit the data, and then the DHT11 to monitor the internal temperature because we are deploying the system in Sri Lanka where there are high temperatures. And then we have another component which is the step up down to shift up and down the voltages because the Arduino needs 7 volts, the other components needs 5 volts, but the source of the energy is a battery of 12 volts. And also these 2 solutions are sharing the same external sensors. We are using the BME 280 for pressure and humidity. We are using the BH 1750 to measure light in terms of lux, and also the DS1820 to measure temperature. And then we have other three sensors. They are engaged, of course, the soil moisture and the wind speed and direction. And now there is the service layer. We are using EastSOS because it's open source. It's currently used by the to manage the hydrometeorological data of the Canton Ticino, and also because it's SOS OGC compliant. But I would like to invite you to the presentation of tomorrow because we have some news. EastSOS 3 is out, and so if you want to know more about this software, you can go to this presentation. And finally, there is the communication layer, which is the parts which transmit the information. We have some requirements. We would like something that with low data consumes, because we are using the GPRS connection. We would like something that is fast, and we would like something with a send response pattern to be sure that the data are sent correctly. So we integrated in the EastSOS a new feature, which is called fast insert to respond to these needs. This is how we send the data. Basically, we read the data from a data logger, then the GPRS is activated, and then the data will be transmitted for 3 times. It means that if the first time is successful, then the other 2 are not needed. But in Sri Lanka, there are a lack of connection also, and so it's useful to have this kind of way to transmit data, because if the data are successfully sent, they are stored in a data sent folder, otherwise in a data not sent, in a data to be sent folder. In this way, you can keep track of the data that we have sent or not. And this is the whole system that we are deploying in Sri Lanka, in the Deduroya Basin. This basin has a catchment area of 2,600 square kilometers. In this area, there are more than 2,006 millimeters per year, and basically the 50% of this total amount of rain is received during the monsoon periods. So it is an area with heavy rainfall events. We have selected 22 locations, basically 18 schools and temples, because in this way we can be sure about also the safety of what we are installing, the weather station. These are some images about the installation process. Many students of the University of Muratura are involved in, and the possibility to install the weather station in schools, elementary, primary schools, is also useful to make a sort of education activity. Of course, when the system is deployed, there is the need to maintain it. So to be something that is easy to use, we are using the ODK, the Open Data Kit, which has an ODK collect application where there is a form to be filled and to guide the maintainer on the maintenance stuff that is needed to the station. And also there is the ODK aggregate, which is server-side, and in this way we can collect all the activities and made some perform some statistical analysis on the way that are on the issues that are present in the weather stations. Basically, every station has a QR code, and the form with the ODK collet has 6 sections. The first one is to give information about the maintainer. The second, to evaluate the general status of the station. Then the third section is about to check the box if there is some holes that can cause some water inside. Then there is the fourth one, to perform maintenance activity on the internal box component, so you can check if the wires are good, if there is some corrosion, and so on. And then the fifth section to check external sensor status. In fact, we are having some problem in corrosion also. And the last one is about the rain gauge calibration that has to be done to keep the data quality in a certain level. But how the prototype works, and to be sure that this is something that is good enough, we compared in Switzerland the 4-ons model with an official weather station of the Canton Ticino. It is called Trevano, and it has a cost of around 4,050 euros. And the 4-ons mode solution has a cost of 450 euros. And we have evaluated the temperature, the pressure, the humidity, and the rain, because the official weather station has only these 4 parameters. These are the tools that we used to make this comparison. Of course, we are using ESOS to retrieve data through the SOS standard. We are using OAT Python library because it is well integrated to the SOS standard, and you can and there is also some statistical analysis, some statistical function that can be used, and also everything is automatized through Python and some scripts. How we do the comparison? We have 10 minutes aggregate time series. Then we make a sort of visual comparison, and we use the coefficient of determination by Pearson to check the goodness of fit between these 2 time series. And then we analyze also aggregated values, daily mean, max, minimum values through the needs of scatter plots and probability density functions. And this is the first result about the air temperature. Here there are only the daily mean values of the temperature. In the top left there is the graph of the 2 time series, and you can see by a visual comparison that is very well overlapped. And also the coefficient of Pearson is very high, so it's really good. The mean error is below 0.3 degree of temperature, and this is also, and you can see this also through the scatter plot and the density probability function. It's very interesting, the graph in the bottom right, because we plot also the trend of the residuals, and we can see that from August to February we have an increased value of the residuals, so an higher error, and probably this is due to a different response of the sensor in the cold or warm season, but we are not sure in this, and only the next winter will answer to this issue. Because probably it could be also a sensor drift, so decreased quality of the measurement of the sensor. This is air pressure, and also here is the results are very good, because the mean error is basically under 0.4 hectopascal. Also, the standard deviation is quite good. And also here in the bottom right, you can see that there is this behavior in this increasing of the error in winter, but maybe with the time. Okay. Here there is the air humidity, which is the worst parameter that we have evaluated, but still good, because from the scatter plot you can see that there is this dual behavior. So when values are over 70%, the humidity sensor of the prototype overestimates value. Otherwise, when the humidity is below the 70%, the sensor underestimates value. So there is this dual behavior. And also for this parameter, the residual seems to increase during the winter or during time. And here there is the most interesting parameter, which is the precipitation. And here we are using the rain gauge by Davis, so it's a proprietary solution, because we don't have other solution, open solution. We are building something that is open, but we have to test it. But the results from this rain gauge, which is the most expensive sensor that we are using, but is quite cheap because it's $100, are very good, because the error, if you compare the total amount of rain, is more or less 6%. And also it's very interesting how the 4-ounce prototype, through the analysis of the data, we have selected 14 rain events, including some snow events, as the official weather station. So also this kind of comparison, in my opinion, is good to see that it can be a sensor that can be used in a real case study. So in conclusion, the results are very good of the comparison of the data. The temperature and the pressure are the best parameter that we are measuring. But also the humidity, but here there are more issues, but probably because of the humidity parameter that is quite not so easy to measure. And currently we have deployed 18 stations in the Duroia Basin, so we are near to start the real case study. So we are starting, we are start to collect data, and for this reason, in the future, we would like to have some extreme event notification system. We would like to send automatically reports that can give information about the quality of the data and if the stations are working. So maybe through daily or weekly reports. And also we would like to use the data for hydrological model, because in the Duroia Basin there is a tank system to laminate the floods, but there is no integration with real-time data, with weather data, and so on. So with the data which we are collecting, it could be possible to use hydrological model to better manage the tank system. And also we have to check this behavior of the residual, to be sure that there is something related to the sensor or to the season.
Any question? Can start it.
Yeah, yes, because we have an how to build the station online. Yes, if you visit the website, you can find it. And yeah, you can build on your own the station. It's easier, the mod solution, because the PCB you need to send the schema to a service that can produce to you the PCB.
Any further questions? Then I will have another question. So you already produced 18 of these stations, and it seems like it's much cheaper than the selected reference. Do you see any business opportunity in mass producing such weather stations in the future?
Well, I don't know, because our solution, we need to see if it's something that can have a life in time, okay? But I don't know. This is an open source project, and so I don't know.
You can build a startup on an open source project,
yeah.
So maybe consider it later. Then thanks again for the presentation. And the authors of our last presentation will be Alan Mangafic, Nika Messner, and Mihaela Cekada. And the topic will be grassland recognition with the usage of thermal weights.
Yeah, it's already.